Okay, so all those scientists that I just brought up that are on our list, they basically take us up till, oh, I can't remember when Chadwick discovered the neutron. For some reason, I want to think one of them ends in the 1950s, but don't quote me on that. It's been a couple of years here. It takes us up through the main initial part of the 20th century. Right? In 1900, Planck discovers quantum ideas. 1909, I want to think, Rutherford works on his model. 1911, we're up to the Bohr model. And as we saw in that one video, from the 1930s onwards, Einstein and Bohr, they were debating which of their models of like reality fit best. And even until Einstein died, there was no right answer figured out yet. So, anyways, as we've been learning in the early part of the 20th century, there were huge advances. Um, One of the things that it really helped out the physics was how to work with chemistry. And so this is one of the lessons that I love the most, is because I also teach you guys chemistry. And so there's a huge amount of overlap in this section. And one of the things I'm going to need you guys to be able to do is just some basic chem, because they might test you on it. Okay, so I guess I'm teaching from here today. Anybody want breakfast? Just joke. I see yogurt. Cheese. Nobody? You guys look really tired. Okay, so what the advances in physics allowed was a way better understanding of how chemistry works. So today we're going to do probably two different halves to our lesson. No, maybe three thirds. The first little bit, we're going to do a little bit of chemistry review to make sure that you all understand the concept of it. Then I'm going to talk to you about three different types of decay and how it's actually possible to change the nucleus of an atom. And then we're also going to talk about the energy required to bind together the nucleus of an atom, because that actually also was kind of perplexing at the time. So let's start off with a slide I've got here right there with just some key chemistry terms. I just want to make sure that you guys are all talking the same language. So first thing, do you guys know what an atomic number is on a periodic table? Say that louder. Yeah, atomic number is the number of protons, right? And if you guys can see the periodic table way in the back there, it's the large number that usually, it's large whole number that goes with an element, right? So oxygen's number 8, hydrogen's number 1, lithium's number 3. It's defined by how many protons it is. And that atomic number literally defines what we call it. You can change the number of electrons, you can change the number of neutrons, but you cannot change the number of protons, because if you change protons, you change its identity. Does that work? Now, mass number is how heavy the item is total. And I'm going to flip ahead to another slide right here, or maybe back, or somewhere here. No, still not what I'm looking for. Here we go. Have you guys ever seen me write chemicals in this sort of notation, where I might say magnesium, and then on the bottom I might put, well, no, I have to put 12 for magnesium, and on the top I might put 25. The 12 is the atomic number. The 12 is always 12 for magnesium. It's always number 12. It's 12 protons. The 25 is its mass number, which is how heavy it is total. If there's 12 protons, anybody know how many neutrons there are? 13, yeah. This number on the top here is the protons plus the neutrons. So that is the mass number of an individual ion. So each individual atom either weighs 12 or 13 or 72 or something like that. And it's really, this is what happens when you add your protons and your neutrons to each other. That gives you your mass number. Now, isotope then refers to what specific mass number you're using. So for example, we can work with carbon 12, we can work with carbon 13, we can work with carbon 14. Those are all considered isotopes of each other. What's the only difference between the three? Yeah, more neutrons, right? Carbon 12 would have 6 neutrons. The reason why it's 6 is that carbon has 6 protons. It's a guaranteed hard and fast rule. So to get to 12, 6 plus blank equals 12. 6 is your answer, right? So you need 6 neutrons. Carbon 13 has 7 neutrons. Carbon 14 has 8 neutrons. They're heavier, but they're still carbon. Sounds good so far? Well, then when you want to talk about the atomic weight or the atomic mass, that's where for carbon it's 12.01. This is the weighted average. So because there's some 12s, some 13s, some 14s, this is what the average seems to turn out to be. But if you were to look at one atom of carbon, it cannot be 12.01. Right? One atom either has to be 12 or 13 or 14. It can't be halfway in between. But we use the decimal numbers in chemistry because of the fact that, I mean, we don't know what the breakdown is going to be. We just know the probability percentage-wise. Does that make sense? We don't use this number, by the way, in physics. This is more of a chemistry type number. In physics, we're going to work on individual atoms. So it's either going to be 12 or 13, but not 12.01 or 24.31. It's either one or the other on a molecular level. What's the difference between an atom and an ion? Electrons, yeah. You can't become negative or positive by losing protons, but you can become negative or positive by losing electrons. So atoms are neutral. They have the same number of protons and electrons. Ions, you'll also find those on a chemistry periodic table a lot, where it'll be like a +2 charge or a -1 charge. How do you become +2? Lose 2 electrons, because you can't gain 2 protons. Because if you gain 2 protons, you're now a different element. And if you want to become negative, then you gain electrons. So loss of electrons, gain of electrons. You guys did chemistry last year, Leo says GER type stuff. Okay, and then the last term on here, valence electrons, those are like the outermost electrons. So if you use a Bohr model of the atom where here's a nucleus, and then you have orbitals around it. I've shown you a video how the orbitals are actually funky three-dimensional balloon cloud shaped sort of things. But if you use this sort of model here, the valence electrons are the one in the outermost electron number. And those seem to be the ones that form bonds. So far, so good. Okay, I've got a whole ton of pictures here just to remind you. Keep this one nearby because when we need to use a periodic table today, we'll use this. On the diploma exam, they will give you a periodic table, by the way. It's a very, very basic one. It doesn't give you a whole lot more than this, actually. Pretty sure all it gives you is just the atomic number for every element, and that's it. So you don't need to have, like, molar masses. You don't need to have charges. All that really matters to you is that you know gold has 79 protons, tellurium has 52 protons. So just try to keep this slide nearby if you don't have the periodic table. Like if you don't know it. I wouldn't expect you to memorize it, but you might know a few of the molar or a few of the atomic numbers, like nitrogen being 7 or oxygen being 8. You might be able to see it on the big table. What was that? That one's allowed to stay there on the test. Honestly, you don't need anything more than just the proton number, though. So just a very, very basic periodic table will do. This is what a more chemistry-based periodic table will give you. The name, the symbol, the atomic number, and the atomic mass are some of the more common things to have. We really don't need the atomic mass, but I mean this just helps you know roughly how many neutrons there's going to be. Because if this is an average of let's call it 96, roughly, and there's 42 protons, then you should know that there's about 54 neutrons. That's my symbol for neutron, by the way, N with a 0, because then it's neutron, no charge. Anyways, that gives you roughly how many neutrons there's going to be, but just know that it's not for sure 54. And then here's some pictures showing just valence electrons and Bohr orbital shells, things like that. Yes, feel like you're okay with the chemistry part of it? I know I've taught all of you chemistry at some point. Okay, let's fast forward here then. So here's where this overlaps with physics. In chemistry, we'll use grams per mole. You guys remember using a molar mass before? Basically, a grams per mole is how much weight does 6.02 times 10 to the 23 atoms weigh. Right? If I were to look up carbon is 12.01. That's how many grams you have in a mole, which is how many grams you have in 6.022 times 10 to the 23 atoms, which essentially is, rather than finding the weight of one atom, it's the weight of a whole bunch of atoms collectively, which makes a lot of sense. However, from a physics perspective, we actually need to talk about things just one atom at a time. So we actually have a physics term that we use to refer to mass, and this is something that you'll find on your data booklet. It's called an atomic mass unit. You guys find that on your data page if you have it nearby there? I believe it's the bottom one in the section on constants. The bottom one? Okay. It's called an atomic mass unit. And basically, one of these things, a U, is defined as a very, very, very small amount. Essentially, an atomic mass unit is more or less it's the mass of a proton or a neutron or something like that. But rather than trying to figure this out like based on moles and how many moles of particles there are, they're defined as, it's actually based on carbon-12. U is based on a neutral atom of carbon-12, which has been defined as having a mass of 12U. Basically, they just said, let's make carbon be like the standard bearer. Had to pick someone to be the standard. And so, therefore, a U is 1/12 of what carbon-12 weighs. And this, it's a little bit silly. I wrote here, it's a little bit silly to measure things in kilograms. So you might see things, measure them in U's. A U basically being a very, very, very small amount of mass. So I pulled this slide out of your textbook. I've seen diploma questions on this before. You wouldn't be asked to memorize this data, but they could give you this sort of data and then ask you to answer a question based on it. So we're going to need to relate back to the slide over the next little while. This essentially is the atomic mass of each of these things, but now it's being measured in U. So like one hydrogen atom is 1.007825 multiplied by 1.66 times 10 to the minus 27. All of these numbers right here, you have to multiply them by 1.66 times 10 to the minus 27, and that's how many kilograms there's going to be. So, but these are like smaller units. And one thing you'll notice is that by putting them into the atomic mass units, one of the cool things is that these things more or less line up with whatever the mass number is. See how like here you have zirconium-94? Well, in atomic mass units, it's basically 94. And krypton-92, 92 is the total number of protons and neutrons, right? Well, the atomic mass number is basically 92. So now it's not exactly, because the biggest reason why is that a proton and a neutron are almost the same mass, except the neutron weighs just slightly more when you get down to sig digs. You can see that on this slide right here, I believe. Here is the mass of an electron. Sorry, it's sideways. It's the way I can fit it on there. And it's to the minus 31. Here's the mass of your protons and neutrons. Look, it's 1.672, and this one's 1.674. Neutrons weigh just slightly more than protons do. Not when you consider sig digs, right? It's sig digs, if you look on your table here, 1.67. But that's the reason why an atomic mass unit is not perfect, is that these two guys right here are like slightly off from each other in terms of their mass. So, but this is pretty close. Okay, so now to a little bit of theory here. We've actually approached this question before. Why in the world does the nucleus stay next to each other? Physicists asked the question, why do those positively charged particles stay next to each other? And there was a theory. And I'm going to disprove this really quickly here. The theory is that, well, maybe all of these items that are in a nucleus, you know how there's going to be some neutrons or some protons, so I'll put a positive in a couple of them here. So a few of them are positive, some are neutral. Well, maybe because they're so closely together, gravity is keeping them close together. Because really, isn't that what gravity does? Gravity takes matter, and it wants the matters to suck towards each other. I mean, electrostatically, the positive and the positive would want to repel each other based on electrostatic force, but maybe the gravitational force would want them to attract to each other. So maybe that's the reason why the nucleus stays together. So, but we can actually prove this very, very quickly here. In order for the nucleus to stay together, you'd have to have your gravitational force be greater than your electrostatic force. And so what I'm going to do is I'm going to write an equation with an equal sign, just temporarily, But keep in mind that what I'm really looking for is this side to become bigger than the other side. So essentially, if my gravitational force is to be bigger than my electric force, this formula right here has to at least be equal to this side right here, if not more. Now, as I consider how this works, first thing I can do is I can say, well, look, there's a radius squared on the bottom of both of them. I don't know how far apart these particles are. We now know that they're far apart by a unit of angstroms, but however far apart these particles are, it's the same on either formula. So essentially what I need to do is I need to make Gm1, M2 be equal to KQ1, Q2. You see how I do that so far? And maybe I shouldn't say, why don't I just do this? It needs to be greater than or equal to, maybe. Equal, I guess, would be like barely sufficient. Greater than would be better. Okay, well, let's start talking about some of these particles here. G, we haven't used this in a long time. What's the gravitational constant that Cavendish is given? 6.67 times 10 to the minus 11. Okay, then we need to know the mass. Well, it doesn't really matter all that much. The mass of the particles in the nucleus are either protons or neutrons. So, I mean, the protons could be gravitationally attracted to the neutrons, but either way, the mass of either of these particles is about 1.67 times 10 to the minus, is it 27? And if it's okay with you guys, I'm just going to square that, because really for these two masses that you have right here, they're the same, essentially, right? For all intents and purposes, the mass of a neutron and proton are both the same as each other. Okay, which means that if I grab my calculator, I'm just going to try to calculate what the left-hand side of the equation is here. 6.67 times 10 to the minus 11. It's multiplied by 1.67 times 10 to the minus 27 squared. I got this. 1.86 times 10 to the minus 64. See that too? Okay, over on the other side right here, we need that gravitational force of attraction to be larger than, maybe we can deal with it being equal to the electrostatic force. If it was equal to the electrostatic force, at least it's like Newton's second law, it's like it's F net equals ma. At least there's, if it's stationary, if the forces are equal to each other, at least it's not going to be that. Okay. So we would need this side right here to be at least as much, but preferably less than. Sound good? So let's try this side. Over here, you're going to have K, which is the constant based on electrostatics, 8.99 times 10 to the 9. And then we need to know the charges. Well, what's pushing each other apart in the nucleus? Protons. What's the charge on a proton? 1.6 times 10 to the minus 19. Now, we do need two of them, but I'm not even sure I need to do the math on this. Look at this. This is a minus 11. This is two minus 27s. This guy right here is a positive 9, and then two minus 19s. I mean, we can do the math real quick just to be thorough. 8.99 times 10 to the 9 times by 1.6 times 10 to the minus 19 squared. It ends up giving me 2.3 times 10 to the minus 28. Is the gravitational force bigger than the electrostatic force? Not even reasonably close. Like, this is, how far? From 68 to 20, 64 to 28. It's too early to do math in my head. There are 36 extra zeros in the one equation than the other one. I can't even fathom how big that is. Like, that's more than a trillion, a billion, a trillion billion, a gazillion. I can't even make up a number for that. Times bigger. So this caused a huge problem then. The idea that the nucleus could stick together because gravity was strong enough to do that was totally not possible. So they needed to come up with a new theory then. Why does a nucleus stick together? And so physicists determined there must be another force. There must be a force that keeps that nucleus stuck together. Because logic would dictate it wants to just bust apart. Right? So it's called the strong nuclear force, which acts over really incredibly small distances. And they figure this must be the strongest of all forces. So we've actually learned about other forces already. We've learned about gravity back in Physics 20. And then we learned about our electrostatic and magnetic forces in Physics 30. Um, we're going to just briefly talk about strong nuclear forces. The theory basically is that, well, there must be some sort of force that works over the smallest of smallest distances that somehow overcomes the desire for positives to repel each other. Okay? And so as long as the nucleus is stable, there must be some sort of energy, right? I mean, if there's some sort of force attracting them together, there must be some sort of energy keeping them together. And this was known as binding energy. I mean, that makes sense, right? Isn't it the energy that binds the nucleus together? I like to think of it as the glue. It's the glue that keeps the nucleus together. Now, some really clever physicists back in 1930s to 1940s started to try to figure out, well, if there's energy keeping the nucleus together, if we can find a way to break that nucleus apart, we could release a whole bunch of energy. And those physicists were working on this it was very relevant in their era because they needed to figure out the technology very quickly in order to stop something. Anybody know what I'm leaning towards here? They needed to stop Adolf Hitler. What were they trying to make? First atomic bomb, right? They needed to try to find a way. The Manhattan Project. You guys ever hear about them before? Enrico Fermi, Robert Oppenheimer. Those names you recognize. They realized that if they could harness the amount of energy that was binding a nucleus together and create an atomic weapon, then that would be the trump card, so to speak, in World War II. And it ended up happening, right? If you guys know your history all that much. Although the Allies did defeat Nazi Germany through things like storming the beaches of Normandy, the atomic bomb, there were two of them dropped in Japan, which, I mean, historians think that might have shortened the war on the Japanese front because that did eventually end World War II on the I don't know, I guess from our perspective on the Western front. Does that make sense? So this is about when was the bomb dropped? 1944, I think, 1945, around then. So in the 30s to 40s, scientists were working on trying to figure out how can they harness this strong nuclear force. And I mean, here's basically a chemical energy diagram that some of you guys should recognize from chemistry. If you begin with some reactants, if you can find a way to break, right here you'd have to break the bonds, that strong bond inside the nucleus. And you need to input some energy. But if you can break that bond apart and you can break the nucleus, all of a sudden that strong nuclear force, it could get released as a huge amount of energy. But this doesn't happen naturally. So you'd actually have to input some energy. Do you guys remember diagrams like this from Chem 30? This would be an input of initial energy to get the ball rolling. And then once that happens, a huge wave gets released otherwise. And really, this was the advent of the nuclear age, which, even in hindsight, a lot of those scientists I just mentioned, the Manhattan Project scientists, they really regretted their work because this discovery of how to harness the nuclear energy, really, it's now put the world in such a bind in terms of, well, now there's always this threat of nuclear war hanging over our heads. Maybe not as much now as it was in like the 1980s, maybe early 1970s, like the Cold War. You guys talk about this at all in social studies? Oh, okay, so you know some of these terms. But anyways, this is kind of the next advent, is discovering how to use the nucleus. So what we're going to do is some basic calculations, trying to calculate how much energy you can actually get from a nucleus of an atom just by rearranging, by pulling out protons. Okay? And Einstein figured out the formula for this. The formula is E equals mc squared. Okay? Now, maybe the best way for me to describe this to you is that they discovered that when a nucleus was stuck together, it weighed more than if you took all the pieces apart individually. It was very strange at the time. Let's say that you were working with helium. We know that helium has 2 protons and probably 2 neutrons. And so they were able to weigh what a proton was and what a neutron was. And they said, okay, well, this is much helium should weigh. I've weighed up 2 protons. I've weighed up 2 neutrons. It should weigh this amount. And then they weighed helium. And it weighed this amount. I was like, hang on a sec. How can helium weigh more than it's supposed to based on the individual pieces? The analogy I would give here is when my daughter plays with Lego. And so I give Kinsey a whole bunch of building blocks, and individually the building blocks I'll weigh this and this and this and this and this. But I'm one of those dads like in the Lego movie who likes to super glue the Lego together when it's done. And so when the final product is made and there's a little bit of crazy glue inside, keeping the Lego stuck together, it weighs just a little bit more. You get that analogy there? And so they discovered, well, hang on a sec, there must be a difference in the mass. The difference in the energy of the nucleus and its individual nucleons is known as a mass defect. And they were able to find the difference in mass between individual pieces on their own and collectively them together in the nucleus. And the reason why one weighed a little bit more is because there was a glue, an energy, so to speak, keeping them together. And then when you break it apart, well, that energy could then be released as nuclear energy. And so this is where Einstein's formula comes from. So I'd like to show you basically in this first example here just how we'd be able to calculate how much energy there would be inside of a zirconium-93 atom. So this is a number that we would have either looked up on a table or they would give you on the diploma. So a while back ago I showed you guys this table way back here. Zirconium-93. Okay, apparently 93 is not on here, but see how zirconium-94 is on here? Okay, this is how much just one atom weighs by being able to figure out the weight of the single one. But it doesn't weigh as much as the individual parts should weigh. So in order to solve this, here's what we're going to do. We're going to find the mass defect by finding the difference between the individual components. So first thought here, we need to know what the mass of the protons in zirconium are, plus the mass of the neutrons. Now, we normally skip the mass of the electrons because you know how protons and neutrons are to the minus 27 and electrons are to the minus 31? That's 4 extra zeros. It hardly makes a difference the electrons do. So usually when we do this, we just calculate mass of protons and mass of neutrons. So first question, we got to figure out how many protons zirconium has. So you either need to look at that back periodic table or look at the periodic table in your notes and you got to find, well, where the heck is zirconium? I believe it's right next to yttrium, which is the Y, which is number 40. Okay, so based on that, we must know that there's 40 protons. Well, then we need to know what the mass of a proton is. Now, for the purposes of doing this example here, I'm going to ignore sig digs. Now, in your data booklet, it'll tell you the mass of a proton is 167, but I'm going to go back to this slide right back here, and I'm going to use the exact number, like even more precision. So it's 1.672622. 1.672622. 1.672622 times 10 to the minus 27. There's your mass of protons. All right, now for your mass of neutrons, we need to know how many neutrons this particular zirconium atom has inside its nucleus. How'd you figure that out? Yeah, just subtract those values. So I'm going to turn these guys down. Yeah, so 40 plus x equals 93. You need 53 neutrons. We now need to know the mass of your neutrons off the periodic table back here. Now I'm going to do the exact mass though, with more sig digs. So neutrons are 1.671927. That's a 4 underneath there. 674927. 674927. 674,927 e minus 27. Okay, so this should then, since we're gonna ignore electrons because we know electrons are so light they should hardly make a difference. But we'll add up now the mass of our nucleus. But this is like when I buy Kinsey on the Lego in the box. This is how much the individual pieces weighed. Okay? So this is before assembling them. This is the weight we should have. So I said ignore sig digs. Let's just write down as many as we've got. I've got 1.55 677,611 e to the minus 25, and that would be kilograms. Let's get that. Okay, and just to make sure that I'm clear on this, this is how much they weigh individually. Individually. I don't know what I just spelled there. It's not individually at all. Okay, let's do this. Apart. That's how much they weigh apart. However, we looked up the mass of zirconium, and zirconium weighed 192 point that number. However, I can't compare these two because they're apples and oranges. How do I get this number here into kilograms? What do you times by? One atomic mass unit is 1.66 times 10 to the minus 27. So then we have to figure out how much they weigh together, which would be 92.90647 times by 1.66 times 10 to the minus 27. That's how many kilograms is in an atomic mass unit. And this will tell us how much they weigh collectively. On this one here, oh, why did this not weigh the same amount? 1.5422474 e minus 25. That number's lower. Oh, I've been lying to you backwards. Sheesh. Okay, this number is less. The reason why it's less is that the excess mass. My analogy fails here. Shoot, my analogy doesn't work so well. The reason why it's less is because that extra mass is what helps glue the nucleus together, right? Because in a way, what you've got is the together plus some energy to keep them together must equal how much mass they have apart. So I guess my glue analogy doesn't really make sense because that would make them heavier. Here's how much they weigh together. See how they weigh more apart? The difference in the mass there must be the amount of energy that you have there. And so that extra energy is really mass. That's where Einstein's formula comes in, E equals mc squared. And so the extra mass that you would have lost right here is really in the form of energy binding them together. So we can actually calculate that by subtracting these two numbers right here, and then the subtraction of those two numbers is the amount of mass defect. Does that make sense what I'm saying here? So the mass of them collectively is actually different from the mass of them individually. They weigh a different amount. The reason why is that the glue that holds them together, the extra mass, is this energy right here. So if I want to use that formula now, we found the mass defect. To find the binding energy, all I'm going to do is subtract these two numbers. So 1.5567711 e to the minus 25. Subtract that number. So I have a difference in mass of basically 1.45 times 10 to the minus 27. Well, Einstein theorized that lack of mass, there's missing mass, so to speak. That missing mass must be the energy used to bind them together. So if you now want to use the formula, the energy there is equal to mc squared, then you just use this number here, the difference in mass, and times by the speed of light squared. And that's how much energy you would get by basically breaking apart a zirconium atom. I got 1.3 times 10 to the minus 10. Now, on your own, you might think, that's it? That's all the energy we're going to get? But I need you to consider the scale here. That's how much energy we got out of one atom. How often are we working with one atom? Not very often. Well, in chemistry, we often work with a mole of atoms. Right? A mole would be 6.02 times 10 to the 23 of these. So is everybody okay with me getting to this number here? That's how I solved that. I found the mass of them individually by adding up protons and neutrons. I was given the mass of them collectively. I subtracted the two to find what's called the mass defect. Well, the gap in mass, Einstein theorized, is the energy holding the nucleus together. So using E equals mc squared, we found that energy. But that's the energy holding one nucleus together. Now, that doesn't seem like a lot of joules, but if you were to take that number and times by 6.022 times 10 to the 23, which is how much a mole is, so this would be in one atom. If you were to times by 6.022 times 10 to the 23, which is how much a mole of atoms is, well, all of a sudden now, a mole is a more standard unit that we use in chemistry. All of a sudden now you're getting 7.89 times 10 to the 13 joules. That's staggering. This would be in 1 mole. I can't see the table from here. Brooke, can you tell me what the molar weight of zirconium is off the periodic table there? Okay. So what this would mean is that if you had 91 grams of zirconium, you'd have a mole. And if you were to able to break apart all the nuclei in that 90 something grams of zirconium, you'd get that much energy, which is beyond a gigajoule. A giga is times 10 to the 9, I believe, right? This would be bigger than that. It would be times 10 to the 12, whatever that prefix is. That's a huge amount of energy, which is, like I said, this is why Oppenheimer and Fermi and the other guys working on the Manhattan Project realized that they could harness this energy. They could find a way to break apart atoms, which we're going to talk about a little bit more on Thursday with fission and fusion. There's a huge amount of energy available here. Does that make sense? Okay, so basic steps. Find individual neutrons and protons. Find the mass of those. Find the collective mass, which you're probably given. Subtract those two to get the mass defect. That's your mass in E equals mc squared. Times by the speed of light, that's how much energy you get. But it's just out of one atom, as opposed to, you never use one, right? Let's try another one. Let's find the mass defect in binding energy for magnesium-24. So I'll go a little bit faster here. Magnesium-24, first thing we should do is we should do 12 protons and 12 neutrons. So those values were, easier for you guys to find than me, 1.672, 1.672622, 1.672622, 1.672622 times 10 to the minus 27, and you do 12 of those. Someone help me out, so I have to flip back. What was the neutron one again? And that's also times 10 to the minus 27. You need 12 of those. So individually, how much do these weigh? I have a grand total weight of 4.017 times 10 to the minus 26. Okay. So that you should be able to do. Now on the diploma, you wouldn't use this exact number that I have here. You'd just use the 1.67. Okay, because that's what they give you for signals. We would then need to compare this amount of mass with the amount of mass that you'd get on a table. And we'll have to go back to our table here. This would have to be given to you somewhere here. Magnesium-24 weighs 23.0 985042. 23.985042. We'd have to times that by 1.66 times 10 to the minus 27. So 23.985042 times 1.66 times 10 to the minus 27. I got 3.98 times 10 to the minus 26. Let me try my Lego analogy again, because I think I didn't do it very well the first time around. The law of conservation of mass exists. We know that. Lavoisier proved it true. Okay? Mass must be conserved. And yet somehow this doesn't seem to fit. This would be like as though I buy Kinsey individual Legos, they weigh this much. I buy Kinsey, I put them together, and somehow collectively they weigh less. Well, the explanation for how separately they weigh more than collectively is the only way to get them to collectively fit together is that somehow there must be a binding energy that allows them to fit together somehow. So that missing mass is not actually mass, it's energy that keeps them stuck together. So subtract these two numbers right here. This guy here, the individual portion one, from this guy right here, and that gives you a mass defect, the amount of missing mass. So 4.017058 e minus 26. Subtract my answer. I have a change in mass of 3.55 times 10 to the minus 28. And then I just make that part of my E equals mc squared formula. What was that? Did you get something different than me? I've been really lazy with my syncing some of my calculator. What did you get? Do you have 4.017 up here? And 3.89 right here? Do we agree on those numbers? So maybe I wrote a number down wrong. Magnesium 23.985042. Yeah, then you times that by 1.66 times 10 to the minus 27. Check this one here. Times by 1.66 times 27. Okay, so you have what I did? Anybody else have what I did? Okay, anyways, if you get the concept here, let's move forward here. Times that number by the speed of light squared. I have 3.2 times 10 to the minus 11 joules. Let's not worry too much about sig digs right here, because really I'm cheating here. I was giving you exact values out of the textbook, whereas on your diploma, they'll be giving you the 1.67 numbers for neutrons and protons. So I got 3.2 to the minus 11. You guys get something similar to that? For the energy, yeah, 3.2. Keep in mind, that number is for one atom. So even though it seems like an exceptionally small number of energy, it's for one atom, right? Which is why a nuclear reactor, since it uses well more than one atom, is able to produce so much energy if it can cause some sort of nuclear reaction. Sound good? Okay, I gotta move faster here. Okay, well, what we've discovered then is if nucleus rearrange themselves and break apart, there's three types of decay, and the word we use is transmutation. This is where one atom changes its proton number. And so calcium becomes potassium, or gold becomes cadmium, or uranium becomes something else. So these are known as the decay. So there's actually three types of decay. There's alpha, beta, and gamma, based off of the first two letters of the Greek alphabet, actually, alpha, beta, gamma. And so I want to show you on the next few slides how these work. These are the common ones. Alpha decay is when an alpha particle is emitted from an unstable nucleus. So the words we use are parent nucleus and daughter nucleus. In a parent nucleus, basically all that happens is it kicks out 2 protons and 2 neutrons. And then the daughter nucleus becomes 2 protons less. So if you can imagine a periodic table, it means that wherever it is on the periodic table, it's going to drop down 2 spots. And in doing so, that radioactivity might emit some energy, which is why it emits maybe some gamma rays, which are very dangerous for you. So now the good news about the alpha particles themselves is that alpha particles are actually fairly large in the grand scheme of things. So it's not the alpha decay that actually hurts you, because the alpha particles you can stop them with like your clothes basically. So let's do a quick example. Let's find an equation for the alpha decay of iridium-168. First, we need a periodic table. We got to find out where iridium is, and I believe it's number 77. Am I saying that right? So that means you need a 168 iridium, and there's 77 protons. Really, that's the only need you have for a periodic table, is just to look up what number it is. Well, what's going to happen here is that the bonds in the nucleus are going to break apart, and some of that energy is going to get released. That glue that's holding it together will get released as it spits out an alpha particle, which we write like this. It's just like the alpha symbol with a 4 and a 2. So then our question is, well, what's the iridium going to change into? It's no longer going to be iridium. What's 2 lower on the table than iridium? Rhonium, Re. Well, there's now going to be only 75 protons left. Now, if you lose 4 out of 168, it goes down to 164. There. This would be known as alpha decay. And this might release a large amount of energy as well, because the amount of energy here compared to the amount of energy here might be less based on mass. So one of the questions I could ask you then is, well, let's go look this guy up in your data booklet. Let's look this one up in your data booklet and this one up in your data booklet. If the masses are not equal to each other, that mass defect could be the amount of energy that's then released. So I didn't actually ask for that on this question here, but I think I do on a subsequent one here. So here's the idea. The process of alpha decay will cause the mass of the daughter nucleus plus the alpha particle to be less than the mass of the original. And so when we find that difference in energy, that's the same thing, E equals mc squared. So when we find the mass of the original and the mass of the other two, the difference in mass must then be how much energy is, quote unquote, lost and then released. So let's try an example here. Uranium-238 is one of the most common radioactive materials. Let's say it undergoes alpha decay. How much energy is there going to be just based on one of these particles occurring? So first thing we have to do is write sort of a chemistry equation. We got to start with uranium-238, and you'll need to know how many protons uranium has. I believe it's 92. Given a periodic table, you guys can find uranium on there? Okay. So if uranium undergoes alpha decay, it spits out an alpha particle. What is the uranium going to turn into then? What's 2 less than uranium? I believe that's thorium, down to 90. And the isotope of thorium is going to lose 4 atomic particles, so that's 234. Well, similar sort of process here to what we did before. We're going to find the mass before, we're going to find the mass after. And it's not going to be the same because that glue that held the pieces together is going to be different. The amount that it was before is different than the amount afterwards. That difference is going to be how much energy is released. So we just need to look these numbers up. So back to the table, which again, you'd be given this table on a diploma question. Uranium-238 is, I'm just going to write this in my calculator here. It's 238.050788. And then we needed thorium-234, which is right here. So that's going to be 234.043.601. And then the other thing we're going to need to do is figure out the mass of an alpha particle. Well, an alpha particle is actually not listed down here on these particles right here. The reason why is that this table actually covers it right here. It's helium-4. Because isn't helium-4 going to be 2 protons, 2 neutrons? So I'm going to write that one down as well. It's 4.002603. So now that I have all three of those numbers here, let me write down their masses now. One more further here. Okay, so the uranium was 238 and change. The thorium was 234 and change. And the alpha particle is basically 4. Now, if I don't write down the decimals afterwards, they sure look at the same. You got to go, right? Okay, we'll talk more later. But I want to make sure I use all of my digits here, so there should be a slight difference in mass. I have a change in mass of 0.004584. U's. I left it in this unit here. You guys able to follow what I did there? Find the mass of the uranium, find the mass of helium, find the mass of thorium, and when I subtract them from each other, it is slightly off. Did you get what I got there? What'd you get? What'd you get? What did everybody else get? You what I have? What you? Okay. Okay. Oh, don't use 4. Like use 4.002603. Right? I didn't write all these down. I used 238.050788. And then I used 234.043601. This was 4.002603. Anyways, I'm splitting hairs because I'm running out of time. You guys get the concept of how we do this then? Once you find the mass defect, this was still in units of U's though. You'd still have to times this by 1.66 times 10 to the minus 27. And then that's your mass times by the speed of light squared. That's how much energy you'd get from a single atom. So I'm sure the fact that I'm off by a little bit probably doesn't change it too much in the grand scheme of things. So let me see what happens here. I got 6.8 to the minus 13 joules, and I finished the whole thing off. 6.8 times 10 to the minus 13 joules. Give or take. You get the same thing? Yeah, like the slight amount of sig dig shouldn't make too much of a difference there. As long as you get the concept, we're okay. Again, that might not seem like a lot of energy, except that's for one atom. Right? You use a mole of this stuff, and it's going to release a huge amount of energy. Everybody clear on the concept? Find mass before, find mass afterwards. Subtract the two, there should be a slight amount. Make sure that's in kilograms, not in atomic mass units. Speed of light, you got your answer. Okay, I gotta move faster. Beta decay. Beta decay, it occurs when things lose electrons. Basically what happens is a neutron turns into a proton and an electron. Very, very strange concept. Neutrons are neutral. Well, what ends up happening is the neutron becomes positive and negative, almost as though the neutral thing can like break into two pieces. It almost makes it seem like a neutron is positive and negative, but like collectively it's neutral. And so this creates what's called a beta particle, and we usually write it like this: 0 on the top, -1 on the bottom, and then B is the symbol. Now the 0 on the top means that it essentially has no mass. Comparatively, electrons are weightless. The -1 refers to how many protons it has. Well, normally you have whole numbers of protons. But an electron, in a way, is almost like a negative version of a proton. So this is how you write a beta particle. So I'm going to do one last example. I'll have to call it a day here. Let's try the beta decay of thorium-238, and then we'll pick this up another on Wednesday. Because really, this lesson kind of merges with the fourth one we do. So, okay, so thorium-238. There's 234. Thorium was 90, right? So here's what's going to happen. This is going to spit out what we call a beta particle. A beta particle is a -1 and a 0. Here's what's happening. One of the many neutrons in thorium is going to spit off an electron and give it an extra proton. So this guy is going to go up to number 91, which I can't tell what its name is, but it's PA. It actually, beta decay causes something to go back up on the table. And it actually keeps the same number of mass, however, because your neutron that changes to a proton doesn't have it lose any mass. It just somehow spits out an electron. This is known as beta decay. And it can do the exact same thing. If we calculate the mass of this, the mass of an electron, the mass of this, we could calculate an energy loss as well. So why don't we pick this back up again on Wednesday, though, because I know you guys are gone tomorrow. So tomorrow, for the 5 of you that are left, we're going to give you a work day. Sound good? All right, well, that's why I didn't schedule anything tomorrow. Okay, we'll talk more later.